And during the Q&A session, you will be unmuted. And if anyone has the queries during the query session, kindly raise your hand and please turn off your cameras. Okay, we'll be asking for the screenshots. When we ask for the screenshots, like kindly switch on your cameras. Okay, until then, please be on mute. Please maintain the decorum of this meeting. And now I request everyone to be on mute, please. Now, let me give the introduction about Mr. Subhash Bayareddy. Mr. Subhash is a civil engineer with over 10 years of experience in water resource engineering. He is a licensed professional engineer, PE in Texas and Arizona, and certified floodplain manager, CFM, with the Association of State Floodplain Managers in the United States. He has worked on the projects in Arizona, Indiana, Texas, and Hawaii, focusing on hydraulic and hydraulic modeling, floodplain delineation, bridge hydraulics, scour analysis, and storm design. Okay. Beyond the academia as well as beyond this contribution, Subhash has been an alumni of Place Institute of Technology and Sciences, and we are very proud that today he has been presenting this in this session. And Mr. Subhash, over to you.
All right, I was able to unmute myself now. Thank you for the introduction, Durga Prasad. I'm really excited to be here on this panel. And first of all, thank you, PACE, for organizing this event. And I couldn't be more proud of my college, my alum mater. So good luck with all the endeavors you guys are on. And with that, I'm going to start sharing my screen and let me know if you guys can see it. It's hard to keep track of the chat while I'm sharing my screen. Never mind. Okay, please text in the chat if you're unable to see the screen. I'm assuming you guys can see my screen.
Yes, yes, we can see your screen, Mr. Subhash.
Awesome.
Okay.
Okay. That today the topic I would like to present with you guys is usage of artificial intelligence and automation in the field of hydrologic and hydraulic engineering. You know, we perform a lot of hydrologic and hydraulic studies with the software that is that's already available to us, but there are newer tools that are coming out every day, as you guys may be aware of. You know, things like ChatGPT, Claude, now DeepSeek. There are a lot of LLMs that are coming up every day, and I myself and some of my team members, we looked into how we can utilize these up and coming tools in our engineering practices, because by and large, they're primarily being used in the computer science industry to automate programming and to aid the programmers with their coding. Although there are use cases for research students, it's my understanding that there are a lot of research students within this group. So I'm sure you guys must have been using these LLMs to help you with the research work, like performing your literature review and summarizing documents and stuff like that. But we tried venturing into using it in our engineering processes. So I'm going to share a couple of examples where we have implemented that with the group. So with that, let me share a brief overview of how the session is going to go. All right. So this is a brief session overview. First, we're going to briefly touch on what artificial intelligence is, and then we're going to venture into the subset of artificial intelligence, which is a large language model. This is the most popular technology out there today. And today we will be primarily working with LLMs. I understand the title says AI, but it really is going to be using the LLMs, which is a subset of AI. It's not the AI. And then I'll try to put a poll here. I don't know how to do that, but maybe you guys can chat in the window. Like, how many of you have used a program called HECRAS, or referred to as HECRAS? If you're in civil engineering industry, focused on hydrologic and hydraulic analysis, you may have heard of this program. I don't know how popular it is in the in India. At least when I was in my bachelor's, which was more than 10 years ago, I was not exposed to this program. But things have changed. We have better internet access these days and better global exposure for the students. So if any one of you have used this program, please chat in the group. So I will be going over HICRAS. I'll be covering a brief, going over it briefly. It's a 90-minute presentation. We should have plenty of time to at least cover the basics of the program. And then obviously, you guys, I'll leave out at least 15 to 20 minutes for Q&A at the end. I expect a lot of questions, especially if you're new to either of these tools. And then we're gonna get into usage of these large language models in the hydrologic and hydraulic engineering. And we have I put together a couple of use cases. One of them is determining erosion protection quantities, like when you're designing some infrastructure. You tend to have, we do, when we're producing flood-proof infrastructure, like when you're building highways, roads across floodplains, one of the key criteria is to make sure these developments are protected for the erosion. And we're going to go over a use case where we can use a custom GPT within ChatGPT to automatically calculate these erosion quantities based on our design files. So that's one case scenario. And then the other one is going to be a live demo where within HECRAS, there is this feature called RAS calculated layer, where you can use hydraulic data output, which is primarily, by default, it produces depths and velocities for the study area. But using those two variables, you can develop further, further, derivatives like scour depths, water surface elevations, everything from there on. So we're gonna perform a live demo. We're gonna go through a live demo where we'll calculate scour depth over a large area, and then we'll also go over an example where how when working with multiple simulation models, how we can use these scripts to generate complex layers. Like you have 2 or 3 flooding sources affecting one area of interest, and but those 2 are created using 2 different models. How can we get a result that accounts for both the models and provides us a bigger picture as to the flood risk for that particular area, not necessarily from one particular flooding source, but every flooding source. So that's how I see the session to flow. Now, let's start with what is artificial intelligence? Well, a simple definition is it's basically machines that can perform tasks normally requiring human intelligence, such as reasoning, pattern recognition, and decision making. A good example is an up and coming technology is automated driving, right? Like driverless vehicles, where these vehicles they perform human-like actions. They drive like humans, uh, using human-like intelligence just for driving. Obviously, we're not in a place where we have Chitti the Robo or Terminator, that sort of stuff. Now, fortunately, not yet. Um, so that you can call that AI also, but today's day and age, the tools that are currently classified as AI or self-driving, now we have these large language models that perform human-like interactions with us in the form of text. They don't have dexterity yet, but they can communicate with us in the form of text. So with that, we'll get into LLMs. So a large language model is basically, it's a subset of AI, which is purely text-based, and they developed it by feeding large text data sets to very powerful computers. And then what it basically does at its core is it predicts the text that comes after a text. So based on your prompt, it using its large data set, I mean, we're talking the entire internet up to 2022 in the text format. So that's a lot of data. So pretty much every concept you can think of, these large language models have been trained on those. So it almost responds like a human, but don't be fooled. It's predicting the text that comes after each text. So a popular example is obviously ChatGPT, 3.5 being the very base version. Now there are multimodal models which can process image and also audio. These some of those examples include DALL-E, where you can give a prompt and it can create an image. Now they came out with a model called Sora, where you can actually create videos out of by giving prompts. We're not going to get into that, but it's just to cover our basics here. Now let's get into HECRAS. So HECRAS is a program developed by the United States Army Corps of Engineers. Within the Corps of Engineers, there is an organization called Hydrologic Engineering Center, and their river analysis system is this program. It's called Hydrologic Engineering Center's River Analysis System. So HECRAS, that's what it stands for. It's commonly referred to as HECRAS, but I just want to let you guys know where it comes from. And what is it used for? It's primarily used, at least within the United States, and as far as I know, Europe, Australia, Canada, majority of the Western countries use this program for performing hydraulic modeling of their man-made and natural waterways. Think about Ganga River, Krishna River, these sort of rivers. You can perform analysis of these rivers and come up with the floodplain limits or flood risk maps for rivers that be as big as Ganga or even as small as Potraj Kalwa in Ongol. So that's the primary application. Now, what does it do? How does it perform the hydraulic analysis? So HECRAS originally started as a one-dimensional steady state modeling software. Now, what does that mean? One-dimensional means you assume the flow is one-dimensional. Imagine a trapezoidal channel. In a trapezoidal channel, the water is flowing in one direction. It's flowing from upstream to downstream. Assume a straight trapezoidal channel. Now, the flow is one-dimensional in that scenario. But I think we can all agree, in reality, flow is anything but one-dimensional. But you have to approximate some of these, simplify some of the variables, because when you get into two-dimensional and three-dimensional hydraulics or fluid mechanics, we're getting into more complex equations, that takes more computation time, and it becomes unrealistic to analyze a large system using three-dimensional analysis. In fact, some of you may know, three-dimensional analysis is three-dimensional fluid dynamics is primarily used for very small scale projects, physically small projects, things like Formula One cars, how they behave through air. That's computational fluid dynamics using in 3 dimensions. So we're talking at such a small scale. We cannot use that sort of technology in a large river system, right? It becomes impractical. Two-dimensional modeling, on the other hand, it's a recent development. Well, I'm jumping ahead of myself. First, let me talk about steady-state modeling versus unsteady state modeling. So we talked about what one-dimensional flow is. Now, steady state means you assume flow does not change over time. So your discharge stays constant over time. You can assume 1,000 cusecs of water going through that trapezoidal channel, and it does not change over time. It's that 1,000 CFS every day, forever. Now that's the scenario you assume in a 1D steady state modeling, where you assume the flow does not change, the peak flow is sustained for a long time, infinite amount of time. And later on, we get into 1D unsteady state modeling. The word itself defines what it is. It's unsteady, which is really how most flows are. It changes over time. So imagine a hydrograph that changes over time. You have rain, the flow increases. When the rain recedes, the flow goes down. So in the same trapezoidal channel of our analogy, you have maybe 1 feet of depth of water flowing through it before the rain. And once the storm gets severe, you tend to see a higher depths, greater depths of flow in the channel. And then after the storm recedes, the water goes down. Now that's the 1D unsteady state modeling. Next, two-dimensional modeling. With two-dimensional modeling, you assume flow can either go upstream to downstream and sideways. It can go left to right, up to down, in both X and Y planes of your physical world. It does not assume flow that goes in the Z-axis, meaning in the direction of the depth. So it doesn't account for hydraulics that occur under the water surface. And there is also another modeling capability within HECRAS, which is rain on grid modeling. This is a very recent edition. In this edition, they have the capability is that you can simulate a rainfall event based on meteorologic data. You can simulate a cloud passing over your project area or your study area, and let the topography and the land use characteristics show you what the effects of the rain on the study area are. So these are the primary applications of HECRAS. As I said, 1D HECRAS assumes flow as one dimension. Flow goes in one direction. To capture that, we use cross sections. So every 100 feet, or depending on the study area, at regular intervals, we draw cross-section lines that capture the channel geometry, as shown in this snippet in the right, over the length of your steady reach. And then we provide the peak flow through the cross-section, and using the average conveyance method, which is basically energy equation simplified for computation. If you guys remember from Bernoulli's equation, that's the energy equation, which accounts for potential energy, velocity head, and then your datum. Those will be solved over an iterative approach between each cross section, and it creates a water surface elevation profile over the steady reach. Like I said, it's one dimension, and it assumes your cross section, wherever your cross section is, it assumes the flow is going perpendicular to that cross section. And it's because it has such limitations. You know, the real world is not a steady state, right? It's not one dimensional, so it has some limitations. You have to pay extra attention to how you draw your cross sections. You need to make sure they're drawn perpendicular to the flow direction, and also the geometry between each cross section need to vary gradually, not rapidly. Let's say you're going through the trapezoidal channel again. If it's diverging into an open field abruptly, it's not gonna be analyzed properly in this 1D steady state. You need to. Oh, audio is not clear. Is everyone else having the same issue, or?
No, we are. It's very audible to us, sir. Please
Okay.
continue, sir.
All right. All right. So the transition needs to be gradual between each cross sections, and it is meant for well-defined channels. It does not work very well when you have a wide flat channel which doesn't have a well-defined waterway. Those are the limitations. Whereas with the 2D model, now we're getting into covering, representing the steady area in the form of a 2D plane. Therefore, you can provide an elevation data set for your entire steady area, and now all of that will be taken into consideration within your 2D geometry. So it accounts for flow splits in smaller areas. You know, I'm showing a snippet here where it is showing the flow arrows as to where the flow is going. Now, if I have to capture this in 1D, I will miss out on flows that are going in the west to east direction. So that's one of the advantages of a 2D model. And also, you're not really relying heavily on the engineer's judgment when you're, whereas in 1D, your engineering judgment is extremely important when drawing the cross-section lines perpendicular to the flow direction, and also the spacing between cross sections, all those things. And 2D models are inherently unsteady, so they always account for volumes, whereas 1D models can be steady state. Steady state means it does not account for volume because it's infinite volume. Now, what data do we need for developing a 2D model? We need terrain. The terrain is an elevation data set. Looks like another user is having audio issues. Is it possible that issue is on your end? Because it looks like the other individual has mentioned the audio is pretty clear.
It's clear, sir. Please.
Okay. Obviously, when developing a model, your model is as good as your input data. And when an elevation data set is basically a raster GIS format, a GIS data set in raster format. When since you're all civil engineering, you all have civil engineering background, you understand when I say cell size, raster cell size, smaller the cell size, more detailed the elevation data set is. That means you have an elevation data point at more locations and at higher density. Now, a 2D model requires the boundary of the steady area, like the area you're studying, it's a polygon boundary. And then you need something called a Manning's N value. Manning's N value is basically the roughness of the surface. Imagine a concrete channel versus an earthen channel. Both will have different levels of roughness, different levels of friction, right? A concrete channel has a lower friction coefficient, therefore a lower Manning value, whereas a man-made natural earthen channel is going to have, a man-made earthen channel is going to have a slightly higher N value, but it's still lower than, let's say, a wooded natural channel. They tend to have a higher roughness. That means they tend to impede flow of water. And you need to provide boundary conditions for the model. Boundary conditions can come in different formats. The new rain on grid is basically, it is applied for the entire model domain, the entire polygon that covers the study area. You can apply rainfall on the entire area. That's one form of boundary. But more commonly, because rain on grid is fairly new, and also when you're analyzing a large waterway, again, I'm going back to Krishna River, which has thousands of square kilometers of drainage area, you cannot simulate rainfall on that entire watershed. But instead, what we do is we take known from flood gauges, from flow gauges, we take flow data and apply that as a boundary condition to the model. And then we need a downstream boundary condition. When the model ends, the water coming in, the mass into the model, which is volume of water flowing into the model through an upstream boundary condition like the hydrograph or the rainfall, that needs to get out of the model. So you need an outflow boundary condition. And there are initial conditions. Now we are getting into nitty-gritty of model development. I don't think we have time for that in this presentation. And then we specify simulation duration, like how long we want to simulate this scenario, and the time step for the simulation. Time step is extremely important because that defines it's a function of your cell size used in the mesh, and also the flow coming through your model domain. It's important because assume you have a cell size of, when I say cell size, when developing a 2D mesh, when you draw the steady boundary, and this I will showcase in our demo. I'll showcase this in our demo. When you turn off, when you draw the steady boundary, you can also look at it. It divides that entire area into squares, like a mesh for a finite element analysis. That's how it, and each one of those cells will be analyzed in the simulation. So when you have a channel with, let's say, with a flow velocity of 20 feet per second, you cannot have the channel represented with a cell size that's under 20 feet, because assuming you are using a 1 second time step, that means every 1 second the water is going 20 feet in distance. So if you have a cell size that's 10 feet and 1 second time step, you're not going to be able to capture the water particle going from one end of the cell to the other end, because the water is going too fast for that time step. So there is a balance between computation time interval and the cell size. The goal is to make sure there is a criteria called Courant number. You want to keep it at one or less. Courant number of 1 basically means your cell size is the same as the maximum velocity, assuming you're using a 1 second time step. And there are several equation sets used for analyzing the hydraulics. But primarily, the two-dimensional modeling, the equation set used in two-dimensional modeling solves for conservation of mass, which is continuity, and conservation of momentum. These are the two laws of physics that are solved in the 2D modeling. And the equation set that is being used for this for solving mass and momentum are the Navier-Stokes equations, but they're being simplified to be able to run in this computation engine. Because when you are to run the original equations in the two-dimensional format, because the original equations are in three-dimensional, are meant for 3 dimensions, but you can simplify it for 2 dimensions, assuming z as 0. There is no flow going up and down. Even at 2 dimensions, you can have more simplified equations that don't account for acceleration of the flow particles and wave physics. That is basically wave propagation within the flood wave. When you eliminate those, that's called a diffusion wave equation. That's the faster way to run a model. When you are first setting up a model, that I typically go with a diffusion wave, and then I go to the full momentum, full equation set that accounts for acceleration and wave propagation. Here is an example of how a 1D model and a 2D model can analyze a channel differently. Here we're looking at a freeway crossing over East Fork White River in Indiana. As you can see in the left side, it's a heat map of the elevation data set. So the red portion is higher, a bluer portion means deeper. You can clearly see the main channel here, but the floodplain is pretty wide. It's about 2 miles wide. That's approximately 3 kilometers. And we have several bridge openings within the floodplain. Now, when analyzing this in a 1D, we will draw cross sections upstream, downstream of this, along this river, and then model the bridge as a one-dimensional hydraulic structure. This is how we'll model it, and then it gives us a water surface profile along the steady reach, and you can get a cross-section view of the flow through the bridge opening. And you can notice here the water surface elevation is constant. That's because it's a one-dimensional model. In a one-dimensional model, it assumes the flow is perpendicular to the cross section, and it can only have one water surface elevation throughout the entire cross section. Now, when you're looking at a span of 8,000 feet, that's not realistic. There is no way it's one constant elevation. So our bridge design is going to be flawed. We might be underestimating the water surface elevation in some areas. We might be overestimating the water surface elevation in another area. And it also means, for example, if it is overestimating the water surface elevation, that means the depth of the flow within the structure is greater than what it should be otherwise. When there is greater depth, it is conservative in terms of the water surface elevation, but it underestimates the velocity through the bridge structure. You can see here in this output, the overflow structures. So bridge 1 is the main one, the bigger one, which it has 81,000 cubics of water going through it, whereas the rightmost one only has 4,000. And the velocity here is 1.7 CFS, which is not the, sorry. Okay. Which is not very accurate, and we'll see why. Now, if we analyze the same system in two-dimensional modeling, we get different results. You can clearly see so the here is a velocity raster. So darker colors mean bluer is the lower velocity, whereas approaching red is higher velocity. Now you can clearly see the overflow structures have higher velocity than the main channel, and that's contrastingly different from what the 1D model showed. So this is just one example to show the limitations of 1D model versus the 2D model. The 2D model tends to do a better job with capturing the flow distribution across a wide floodplain better than the 1D model. And it also provides this beautiful animation that shows you where the flow is ineffective and the direction of the flow. So you can see here the velocities are about 5.5 feet per second in the main channel at its highest. And then when we go to the overflow structure, and we should now pan there shortly, you'll see it gradually increases in the overflow structures. Look at that. That's almost 8 feet per second, approaching maybe 9. Yeah, there is 8 feet per second, 8.5. Okay. All right. Now, is HECRAS the only program that does this two-dimensional modeling? No, there are other programs out there, but this is an open source program. Anybody can download it from the Army Corps of Engineers and play with it. And it's a mesh-based 2D model, which means you can see on the right, they're not perfect squares. You have polygons that have more than 4 sides, whereas on the left side, you have a squared mesh. Now that's a grid-based model. A grid-based model, what it does, grid-based 2D models, there are plenty of programs out there that do grid-based 2D modeling, like Flow 2D. I believe XP Swim is also a grid-based model. SRH 2D. There are, I believe SRH 2D is not a grid-based model, but Flow 2D is a prominent grid-based model. The limitations of a grid-based model are, imagine you have a roadway, like it's shown on the snippet on the right. You want to capture the high ground of that roadway. A mesh-based model will put a cross-section line, a face of the cell along that ridge or crown of the roadway, and you can enforce. You can do so by drawing break lines. A mesh-based a 2D mesh is very versatile. You can manipulate it so that you can have a face wherever you need it, and when you have a face, that means it captures the high ground. Whereas in a grid-based, that entire grid only has one elevation. It's not a cross section. It's one elevation. Anyway, so at the end of the day, all these models are models. They're not reality. But some models, they say all models are wrong, but some are useful. So our goal is to create a model that best represents what could happen, and use that model to come up with action steps. Now let's get into usage of large language models in H&H studies. The case scenario, use case 1, as I mentioned at the beginning of the meeting, determining quantities using ChatGPT. Here, what we will do is we'll provide a base file that's a design drawing into the custom GPT that I created to get a summary of quantities in a spreadsheet format. And then we'll compare, and then that spreadsheet can later be used to compare with the construction drawings. So the input is CAD file that has the design drawings, and the output is a summary of spreadsheet in the form of spreadsheet. So these are the steps that are involved. So this is a more thorough case. I went ahead with the entire process where we will be processing the PDF also and then comparing the results. But for the sake of given the time constraints, I will be going over using ChatGPT to give us the quantities, and we'll stop there. We're not going to get into the design drawings in the PDF format and how these two can be compared. But really, for the objective of this meeting, if we get to getting the quantities using the LLM, that meets the objective of what we're trying to do here. So to do that, we need to convert the CAD file into a GIS readable format, because as of now, ChatGPT cannot read Civil 3D or MicroStation, which are basically CAD files, but it can read GIS files using QGIS that are developed using QGIS and ArcMap. So when we provide the GIS readable format data to ChatGPT, it performs spatial analysis within the GPT, and then perform data interpretation, and then provide us the quantities. So step one, I'm going to take my CAD file and convert it into GIS data. You can easily do that by importing it into ArcMap. You can drag and drop a DWG file into ArcMap. DWG is the format that AutoCAD or Civil 3D uses. And here, what we're looking at is it's a residential development out in the boonies, out in the desert. And when you're building, I'm showing the proposed lot layout here. As you can see, when you build that close to the existing wash, you need to protect the development for erosion against it. I'm going to step out of the presentation for a brief second. I want to give an overview of the project first so that it's better understood. So here is the project. It's currently undeveloped, but this is the proposed grading. We will be raising the ground, blocking the flow, routing the flow around the lots, and then when we do that, we need to protect against erosion due to the flows. And here is a model that shows that's proposed. But first, let me show the existing. So that's the existing model results based on our hydraulic analysis using the two-dimensional model, and that's based on the existing topography. Now, when we switch to the proposed topography, go through the project site. It's going to go around it, obviously. So we are changing the flow patterns. We're forcing flow around the development, and we identify areas where we need to provide erosion protection based on the velocities. Based on the flow velocities, we're going to identify areas where they need protection and what type of protection. So here, going back to the presentation, the highlighted part are our bank protection. Now I have that in the CAD format. I need to quantify that. So what I do is I convert it into a shape file, and then I provide a prompt to the GPT asking, hey, this zip file contains these inches of bank protection, and in that shape file, I have a reach type that classifies what type of the type of reach, basically classified as A, B, C, D, and E. And I wanted to determine how much of each reach, how much area each reach covers, each type of bank protection is covered by, and also the quantity of it. And it should provide me an output like that spreadsheet table, where it gives me the total area per reach and the volume of that quantity, the rock. So this is a custom GPT I created, and we will be looking at, we'll be providing that prompt, and then provide the zip file. Determine the total area. I only ask for total area at this moment in the first prompt. So it's going through the zip file, extracting every file within the zip file. So you can see there is bank protection, all the shape file and its supporting files are being extracted. Now it's reading the shape files using the appropriate libraries. And it provides a summary of the area covered by each reach. Now I want the volume of it. For the volume, I need to provide thickness, like how deep the rock is. I'm asking you to assume 12 inches. So then it does the simple math, area times depth, that's your volume. And not only it does that math, but it also converts it into, instead of cubic feet, we asked for cubic yards, and it also does that conversion on the fly. So that's one use case. Now, the second use case, this is going to be a live demo. We're going to be walking through it together. Generating automation scripts for ICRAS. I'm going to get out of the presentation and then share my screen. For this example, I'm going to share a project we have worked on. This is a solar power project, and we are in an area in Arizona which is primarily a desert. So there is a lot of sunlight and a lot of scope for solar power. And this black outline right here, that's the area that will be covered with solar panels in the future. They're building today as we speak. That entire area covers approximately 1,000 acres. And after completion, it's expected to produce more than 200 megawatts of clean renewable energy. But you can see it is right next to a major flooding source. It's called North Santa Cruz River. This North Santa Cruz River, the proposed project lies within the floodplain of North Santa Cruz River. So we have to analyze how these the posts that hold the solar panels, how they will be impacted with this when there is a flood in the North Santa Cruz Wash. So we developed a 2D model using HICRAS that analyzes the hydraulics of the North Santa Cruz Wash. But in addition to North Santa Cruz Wash, there is the North Santa Cruz Wash, by the way, comes from the southeast corner, enters the area of interest from the southeast corner, and it flows northwest in this direction. And we also have another flooding source from these mountains that comes from east. So we have two flooding sources that impact the project site. We need to take both of those into account in determining the flood risk for these solar panels, so that they can raise the panels high enough and the posts deep enough so that they don't get destroyed during a flood event, during a 100-year flood event. I'm going to go to the model now. Mhm. Okay, here I'm looking at water surface elevation profile, water surface elevation for the model domain from each flooding source. Now we have flooding source number 1, which is the Santa Cruz River flowing from southeast to northwest. I just want to illustrate the flow pattern just for your understanding. You can see it's flowing from the southeast to northwest. If I animate that, you can see the flood inundation. Now that's one flooding source. And we also have the other flooding source called Totalita. So that's Totalita. Now I want to create a layer, a water surface elevation layer that is the maximum of, that's a result of maximum of both these flooding sources. So let's say this area has 1897 resulting from 1903 water surface elevation resulting from Totalita, and less than that from Santa Cruz. I want the highest of the water surface elevation to be shown in that area so that I can tell the contractor to put the panel above that maximum water surface elevation. Now, how can I do that? So the HEC-RAS has a new feature called calculated layer, where you can code, you can provide a script to generate, you know, layers derived from your input. You can create more output by performing math operations using the script. I'm not a programmer myself. Most engineers are not, but we can use these LLMs to help us accomplish it, because I know the process. I just don't know how to do it in the programming language. So here, my input is going to be the two water surface elevations, two maximum water surface elevations from the two flooding sources, and that is Totalita. So I'm going to call it variable 1. I'm going to go for the maximum here. So V1, that's V1. And the second one, Santa Cruz River, that's V2. So I have two variables, and I want maximum of those two, the result layer to show the maximum of those two. I'm going to go to ChatGPT here, and here is the prompt. And the prompt, I just didn't want to waste my time typing the prompt. I'm copying and pasting the prompt, and this prompt is basically what I just described. And this is a new window in ChatGPT. We're starting from scratch. I'm working in HEC-RAS RAS mapper. Update my RAS script for creating a calculated layer where the end product is the highest of the two input layers. Here is the script I have so far. When I have the when I added my inputs, RAS already populated some of the code for me, but it still doesn't know what the operation should be, because I only gave it input. I didn't tell it what steps to take and what output I need. So this script as it is right now is useless to me. But I'm going to give that to ChatGPT. I'm going to give it, and I'm going to ask it to create the right code for me, which is basically this portion. So it's tweaking the script now and it follows the right syntax. It already recognizes what the what the language is based on the syntax. And I go here, I copy that, paste this, and then call it max water surface elevation. And I check the code. Code is compiled successfully. And I'm going to turn off the result layer here so that we can see our calculated layer. So this is our calculated layer. Now it covers both the models. So that's why it has a larger extent. Why is it all blank? Because you can see the number, it has the data. It's just shown differently. It's just everything over 100 in elevation is shown dark. And obviously, if we are, our ground elevation here is 1800. So everything, the water is going to be higher than that. And that's why everything is dark. We can change the color the symbology to match that of the result layer. So I'm going to copy this symbology. And I'm going to turn off the results. Now it created me a composite water surface elevation layer. You can see the contours beautifully, the 1 feet water surface elevation contours. And I can now tell the contractor, hey, you have to be above at least 2 feet above this elevation in this location. And they don't have to use one constant elevation. They can use varying elevation based on this output. And another demo we're going to go through is, as I showed here, this is the area where they're putting the solar panels. So one of the considerations is you need to calculate the scour depth for each of the posts that carries the solar panel. And how do I do that for the entire area? I mean, I have thousands of posts that go in there, and I can't give each post its scour depth individually. That just doesn't, it's not feasible. But instead, if I provide them a scour depth map, a map showing possible scour depth over the entire area, they can use that and say, hey, this entire area we're gonna bury the posts at least by this amount of depth, which is usually greater than the scour depth. So for that, we need to calculate scour depth. And that's not readily generated by HICRAS, but we can again use that script to generate scour depth. For this, we're going to use the CSU Pierce scour equation. For those of you who are not familiar with it, CSU Pierce scour equation is used for calculating bridge scour around bridge piers, which are not abutments, but the columns that hold the bridges. And we have that equation already derived by the experts. There are correction factors that we need to apply for based on the pier geometry, based on the bed condition, but we can make an assumption of those correction factors given that we will be working with same geometry of the posts. They're all circular in nature. So we can use, when it is circular, the angle of attack is always, it doesn't matter because it is circular. If it's a square column, your angle of attack means the direction with which the water is approaching the column. For a round column, you can come from any direction. It's the same effect. Whereas for an elongated elliptical column, that might be different. But we have circular columns here. So my correction factors for the pier nose shape, angle of attack of the flow are going to be constant. I don't have to change them over the area. But if I really want to get that detail, I can also create a raster layer that covers these correction factors based on the location. We're not going to do that here. So what I did is I put together the scour depth equation here. And it's basically a simplified form of this pier scour equation. As you can see, the input I need is the depth of flow and the Froude number. And we have those from the readily available within HECRAS. So within the results section, you have depth, water surface elevation, velocity, and among other things, there is a fluid layer. Okay. Calculated layer. Okay, now my input is going to be max depth, and then fluid number. So these are my V1 and V2. Now I'm gonna tell ChatGPT, hey, I want to calculate the Pierce cover. This is the equation for Pierce cover, and these are my variables, V1 and V2, and V1 stands for depth, V2 stands for fluid number. I'm gonna tell it that, and I'm gonna ask it to create a code that performs the Pierce cover calculation. And that's exactly the prompt I wrote here. And we can continue that chat that was that we already initiated. So I come here. I also need to create another layer for Pierce cover. The equation for Pierce cover is as follows. I provide the equation for cover depth, Pierce cover depth, and then I tell it y is the depth, fr is the fluid number, because that's the nomenclature I used in this equation. And then I correct it saying in the code, V1 is Y and V2 is fluid number. Okay, so I create this cover depth. First, I'm going to change the symbology because my client wants everything under 1 feet to be classified for every 3 inches, which is 0.25 feet. And everything over 1 feet, I can go half a foot interval. So as the flood wave approaches, we can see this cover depth change over the model domain and in depth at each location. So I can clearly identify some of the riskier areas. I can see this area being prone for greater cover depth, and we provide them that data, and so that they can make sure the solar panels that fall in this region can be buried deeper than other locations. So that's my demo. As you can see, if I had to do this by hand, that could have taken much longer. Obviously, this is not created by ChatGPT. It only helped us with the code, but those are some of the use cases. We can use these automation tools in our workflows. So with that, I will open the session to Q&A.
I think that's a good session, Mr. Subhash. Now, I request participants, the chat box is open for you, as well as you can unmute yourself to ask the query. Please raise your hand so that Mr. Subhash can take in order.
I had to stop sharing my screen to see the questions. but I can bring up the screen as needed.
Dear participants, our resource person is open for Q&A session. I request those who have any queries, they can put up on the queries now. Okay, if there were no queries at all, let us conclude the program, and thank you, Mr. Subhash Bayareddy. And to tell you that Mr. Subhash Bayareddy is my BTech classmate, as well my buddy too. Thank you for joining the session, Subhash. That was a very good session, and you have taken from the roots to the depths of hydraulic analysis using AI, and the ease you are using the prompts to the chat GPT to, to get that from the software is fantastic. And thank you for joining us. Our Department of Civil Engineering will be very honored that we have you as the alumni, and let our connection will be connected at all, and all the participants, those who are wanted to fill the feedback, their feedback will be given in the chat box. And with this, let me conclude the session 1. Thank you, Mr. Subhash Bayareddy, for joining us.
Yeah, thank you, Durga Prasad. It's been a pleasure hosting, presenting at this forum. I do think at one point during the presentation, I saw the chat being restricted. Is it possible that it was not enabled?
No, now the chat box is enabled. Actually, we think, and we have communicated through the WhatsApp group about the queries. Till then, we have stopped the chat box here to not to disturb your presentation, Mr. Subhash.
Okay, no worries.
Okay.
Yeah, thank you guys, and hope you guys are doing great. This is a great initiative by PACE. It's a wonderful thing you guys are doing, and investing in the growth of our faculty and research students. That's amazing. I'll be more than happy to contribute my fair share going forward. So thanks for having me on the panel. I appreciate it.
Thank you. Thank you so much, Subhash.
Bye.
I request all the participants, please fill your feedback forms. Okay. And I request all the participants to be more interactive. And if there was any problem from our side, we'll be setting it done. But we have new people to be interacting with us. And thank you for joining us. And the next session will be on the same link. The session will start in a while. Okay, our resource person will join you. Okay. Till then, for the next session, we don't restrict the chat box. But if you have any queries,
the chat box is not visible, sir.
It was enabled now, sir. Actually, the presenter asked to wait for the queries. That's why we have made it disabled. From the next session onwards, your chat box will be visible to you.
Okay. But where is the feedback, sir? Feedback link?
It's in the chat box, sir. We have shared in the chat box feedback link. Please see the chat box once. Request all the participants to stay in the same link itself. The second session is going to start in a while. Okay. Kindly do not get exited. Please stay in the same link. Thank you.
Sir, chat box was not showing, sir, here.
Not, ma'am, some of the participants were posting in the chat box now. The chat box is visible actually.
I can't see that one, sir. If
Madam, it is on
possible,
extreme
please
right
send
hand.
in WhatsApp.
Madam, it is on extreme right hand.
Sir,
Extreme
chat
right
box is
edge.
not visible, sir. Chat box is not visible in the laptop.
Ma'am, it is on the extreme right bottom. Ma'am.
Myself, Sunda Agarkar. Earlier,
Yes, ma'am.
the chat box is not visible, but I
Yes.
rejoined the meeting. I left the meeting and I rejoined it. After that,
Okay.
I'm getting the chat box.
Hmm.
So try that one, if possible. Rejoin the meeting with the same link. You will get the chat box there.
Dear participants, the WhatsApp group will get the feedback link. Kindly fill
Yeah, please,
because
please post it on the WhatsApp group as
yes,
yesterday. No?
yes. It's going in the WhatsApp group, but it's going to be not longer. It will exist for less than 10 to 15 minutes. Kindly fill the form
Okay.
as soon as possible.
Okay, okay. Yeah, I am feeling that, but earlier it was not visible in the meeting, so I rejoined it.
Okay.
Then I'm
Okay.
getting that link in the chat box.
Okay. I think now everyone can see it.
Yeah,
Thank you.
maybe. Yeah,
Thank you for the.
thank you.
Hello again, everyone. I forgot to mention earlier, if you have any questions, you can you can send those questions to the coordinator. They'll reach out to me. Even after the session, that's fine. I'll try to respond to your queries via email through the coordinator.
Dear Subhash, Mr. Subhash, can you save that PPT on the organizer's mail if you can?
Yeah,
Some
sure.
of our audiences.
It cannot be shared via email because of the video content in it, but I'll send a link, a SharePoint link where you can download it.
Yeah, sure. Thank you. Thank you for considering.
Not a problem.
Hmm.
Anything else?
Anything from the participants? Okay. I hope nothing more. Thank you, Subhash. Thank you for joining.
Right. I'm gonna hop off now. Thank you.
Thank you.
यार आया हूँ तो मोबाइल चलाना यार, दिस इज नॉट फेयर यार. ऐसे बोलता है आया करो तो आते ही मोबाइल चला के बैठ जाता है यार.
You just exit. I talk to them.
हेलो हेलो मम्मा. हाँ ये फोन चला रहा है, सुन नहीं रहा है
Mr.
मुझे.
Lalit Kumar Gupta, can you please mute your microphone?